Hello everyone and welcome back to today's Explainer. I am absolutely thrilled to have all of our St. Paul American School Clark 9th grade students joining in today. We have a fantastic, highly focused session ahead of us. Our exact production title for today is G9, Geometry, U01, L3, Congruence as a Geometric Relationship. Basically, we're going to take a concept you probably feel pretty comfortable with and elevate it to a much more rigorous academic high school level. I promise you, by the time we wrap up, you're going to see geometry in a completely new light.
Okay, let's dive right into this. Here's our roadmap for today. 1. Objective, defining congruence. 2. Explanation, sequences of rigid motions. 3. Example, mapping geometric figures. 4. Misconception check, reversing the sequence. 5. Formative check, test your knowledge. And finally 6. Recap, core concepts of congruence. Let's get started.
Section 1. Objective, defining congruence, transitioning to high school geometry.
So, our primary goal today is really about upgrading our understanding. I mean, you've definitely heard the word congruent before, right? But today, we're taking that super familiar idea and subjecting it to a much stricter standard. To see why we even need an upgrade, let's look at this comparison. On one side, we have your classic middle school definition. Two figures have the same size and same shape. Now, as our source material points out, that's intuitive, sure, but frankly, it is mathematically inadequate. Why? Simply because it lacks precision. You could totally have two triangles that appear to have the same size and shape to the naked eye, but mathematically, their side lengths might be just slightly off. Basically, looking the same just doesn't cut it in high school geometry. We need an exact, bulletproof definition, which is that congruence is defined by a sequence of basic rigid motions.
Section 2. Explanation. Sequences of rigid motions. The mechanics of congruence.
So, the crucial point here is understanding the exact mechanics. What does it actually mean for two figures to be congruent? Let's look at how rigid motions build this relationship. Here is our new formal definition. Congruence, which, by the way, is denoted by that really elegant symbol right there, an equal sign with a little tilde on top, means that a geometric figure is congruent to another if and only if there is a sequence of rigid motions that maps one exactly onto the other. We are anchoring a very abstract concept into concrete actions here. You have to physically or mathematically move one shape through space using translations, rotations, or reflections, or some combination of them until it lands perfectly, and I mean perfectly, on top of the other.
Now, because a sequence of rigid motions is really just a mashup of individual basic rigid motions, the whole sequence inherits the rules of those individual motions. This gives us three absolutely vital properties of congruences, which we call C1, C2, and C3. First up, C1. A congruence maps a line to a line, a ray to a ray, a segment to a segment, and an angle to an angle. Everything matches up. Second, C2. A congruence preserves the lengths of segments. And third, C3. It preserves the degrees of angles. Think about it. If a motion stretches, shrinks, or bends the figure in any way, it's not a rigid motion. And if it's not rigid, it is definitely not a congruence.
Section 3. Example. Mapping geometric figures. Seeing congruence in action.
And this brilliantly illustrates exactly what we've been talking about. Now that we have the rules laid out, let's look at a practical application. Check out that rather complex, kind of jagged figure on the left. We'll call it S. We want to prove that it is congruent to the figure on the right, S prime. Under our new rigorous definition, we can't just say, well, they look the same. No way. We have to find a very specific sequence of rigid motions that perfectly overlaps S onto S prime.
So let's break down the exact sequence of motions that gets us there. Step 1, we translate, or slide figure S along that vector you see, vector MN. This shifts it right over, closer to the line of reflection. Then, step 2, we reflect that translated figure across the vertical line L. If you follow those two exact steps, a translation followed by a reflection, the original figure S maps exactly, point for single point, onto S prime. Because this specific sequence exists, we have mathematically, irrefutably proven that S is congruent to S prime.
Section 4. Misconception check. Reversing the sequence. Does it work backwards? Okay, I want to pause here and prepare you to challenge a really common assumption about geometric mapping. It's a great question. If figure S is congruent to figure S prime, meaning we successfully moved S onto S prime, do we know for absolute certain that S prime is congruent to S? I want you to take a second and actually think about the logic here. Does mapping one way guarantee that we can map it back the other way?
Well, the answer is a massive, resounding yes.
every single basic rigid motion can be undone by another basic rigid motion. Congruence is totally a two-way street. Let's think about it. If you translate a figure along a vector, you can just translate it right back along the exact opposite vector. If you reflect it across a line, reflecting it across that exact same line a second time just undoes the motion. If you rotate it clockwise, you just rotate it back counterclockwise. Because literally every step can be reversed, if S maps to S prime, then you better believe S prime maps right back to S.
Section 5. Formative check. Test your knowledge. Apply what you've learned.
Let's move to a quick knowledge check and see how this all builds together. We're going to apply what you just learned to a couple of examples, straight out of our source exercises. Now, what's really interesting about this slide is the contrast. We have two distinct scenarios, each showing a pair of gray triangles. Just using your observational skills and keeping our brand new high school definition in the front of your mind, take a good look at these figures.
So, here's the question for you. Based entirely on the visual side lengths, which pair of triangles literally cannot be mapped onto each other using rigid motions? If you look at that second pair, it is fairly obvious that the sides of those two triangles are different lengths. And what did we just learn about the properties of congruence? Specifically, property C2 tells us that a congruence strictly preserves the lengths of segments. Because these side lengths are clearly different, there is absolutely no sequence of rigid motions, no amount of sliding, flipping, or spinning that could ever map one onto the other. Therefore, for sure, they are not congruent.
Section 6. Recap. Core concepts of congruence. Summarizing today's lesson.
All right, fantastic work today, St. Paul students. We've successfully laid down some strict, rigorous boundaries for this concept. So let's lock in these key takeaways. First up, we are officially ditching the same size, same shape definition. Congruence absolutely requires a sequence of basic, rigid motions that maps one figure directly onto another. Second, congruence strictly preserves both angles and segment lengths. That's our C1, C2, and C3 properties in action. And finally, number 3, the congruence relationship is completely reversible because every single rigid motion can be perfectly undone.
Before we wrap, I want to leave you with one final thought to chew on. If congruence relies entirely on these physical, step-by-step sequences of rigid motions, just look around you. What complex objects in the real physical space of your world could you prove to be mathematically congruent right now, using translations, reflections, and rotations? It's pretty amazing to think about how this rigorous mathematical definition literally governs the architecture and design all around us. Thank you so much for joining me for this explainer. Keep observing the geometry in your world, and I will see you next time.